Alright, welcome to my YouTube channel. Today our lesson is based on plane stresses using Morh's cycle. Plane stresses using Mohr cycle and plane stress formulae. So in other words, we are going to calculate stresses that will act on a certain plane, and then to calculate those stresses we are going to have two options: whether we're going to use analytical method, which is using the formulas, and then we can use graphical method, which is this one of Morse cycle. So this one I take it as lesson 2 or part 2, since I do have first lesson about this stress transformation or Morse cycle thing. So in this one, that means I won't go much into the basic things or into introduction. So the basic things are covered in lesson 1. Right, so let's check this problem here. Stresses acting on an element A in the web of a train rail. So this is the train rail. So you know that the train will have to move on top of the railway. So that railway will be made from the steel. That steel material will have this profile here, this kind of profile. So this will be the cross-sectional area of that rail. So this is the side view or the front view. Now this is what we call element, this whole thing here. So this element, it just represent a particle or a portion of this rail material. So we're going to consider certain particle from this rail material and then enlarge it or exaggerate it, as you can see it here. So this one we magnified this thing so that we can analyze this thing nicely. So this is okay. Here they're talking about element A, meaning that this is the element. I can call this one element A. So which is this one here. Is found to be 40 MPa in tension or tension along the x-axis. So we're going to take this direction. Yeah, let me try to put it here. This one is y, this one is x. So along the x-axis, we're going to have the tensile stress of 42 MPa. So as you can see, these arrows, they are pointing away like this. So we're going to have tension along the x-axis, along the x-axis. Also, we're going to have 140 MPa compression along the y-axis. So this is y, parallel to y, we're going to have 140 MPa compression or compressive. So that's why you'll see this arrow and this one, they will go like this, meaning compression. So this element or this train rail is going to experience a compressive external force due to the weight of the train. So the train will move on top of this thing. So that train will exert a downward force on this rail. So that's why we're going to have these arrows squeezing. So this this rail is going to experience the compression. So as it gets compressed like that due to the weight of the train, as well, this rail is going to stretch or expand in that direction. So which is this direction. So with this magnitude, 42 MPa. Right. Now we're going to find what we call the plane stresses. So this thing here, this one, this is what we call a plane. So here we have a horizontal plane. This one, it's a vertical plane, meaning that we are going to find the stresses that are going to act here along this plane. So along this green plane, we are going to have two stresses. The stress or force that will act parallel to this plane. So that force or that stress that act parallel to this plane, we are going to call it the shear stress. And then the force or the stress that acts perpendicular to this plane here, we are going to call it normal stress. So what is going to happen here is that we are going to incline this element or rotate it from here to there. So once you rotate this element from here by this given angle, 48, in an anti-clockwise direction. Remember to check whether this thing will rotate, is rotated in clockwise or in an anti-clockwise direction. You must make sure that you measure your angle from this vertical line. So you check from this vertical line, you go to this PP line. Then you'll see that moving from here, going to there, you will be moving like this direction. So this direction, which is anti-clockwise direction. So we're going to take this thing and rotate it in an anti-clockwise direction with this angle of 48. So that's what we're going to see now. So now we will be looking for stresses acting on this plane, which is the inclined plane. So now this plane is no longer straight. Remember this thing initially it was vertical plane like this. Now is inclined, or they can say is oblique. So or it's slanting. So we're going to find stresses that are going to act on this plane now. So when we check this stress of 42, which is this one, is no longer normal to this plane. Remember when we say the stress or force is normal is when the force and the plane forms 90 degrees. So this one and this one, they form 90 degrees. Therefore, that's why we say this 42 is normal to this plane. But when it comes to this yellow force or stress together with this green plane here, this angle here is not 90 degrees, it's an obtuse angle. So meaning that this green force now is no longer normal to this green plane there. Now once this thing gets tilted like that, the 42 is no longer normal to this plane, or is no longer perpendicular to this plane. So the one that will be normal to this plane, or the stress that will be normal to this plane, is going to be this one. So this is what we call the new normal stress after rotating this element by a given angle. So this is going to be our normal stress after rotation. Why is it normal? Is because this force and this plane, this green one here, and this one, these two are going to form 90 degrees. Now we have the formula to calculate this stress, this normal stress after rotation. I'm going to show you. And then we're going to have the shear stress as well after rotation. So this 60 that you see here is the shear stress. This is the shear stress. But this is the shear stress before we rotate this element. So after rotating the element, the shear stress value is no longer going to be 60. It's going to change to a certain value. So to calculate that shear stress, remember the shear stress we can say it's caused by the sliding force. The sliding force will be the force acting parallel to the plane. So the stress that acts perpendicular to the plane will be normal stress. The one that acts parallel to this plane, to this green plane, is going to be the shear stress. So calculation wise, if you want to find the shear stress, you have to resolve this thing into components. This one into this component parallel to the plane, this component parallel perpendicular to this plane. Then we'll take this one parallel to the plane divided by this area here. You will get the shear stress. You take this component divided by this area here, you will get the normal stress. Okay, so what you will see is that as you rotate this element, the shear stress and the normal stress, the values of the normal stress and the shear stress will transform, meaning that they will change from a certain value to a certain value as the element gets rotated. So we'll be trying to find those shear stresses on the plane as we rotate this element. So now in practice, why are we trying to find those stresses? Let's say you have this rail, and then at some point, due to maybe certain reason, or you know that the rail is too long, so it means that at some point you have to join the rails. So let's say when you join these rails, you will join them at an angle or at an incline, as you can see. So we're going to weld them like this. So now we will be trying to find the stresses that will act along this weld or this joint. To find those stresses along this plane, inclined plane, we are going to use this method that I'm going to show you, which is either using Mohr cycle or the plane stress formula. So in practice, we use this method to find the stresses along the joint, especially the joint that will be inclined or that will be at an angle. So you will find the stress that will develop there, which is going to be the maximum stress. Then after that, you can compare that maximum stress with the strength of the weld. So this weld that you are going to find there is going to have a certain strength. So you will take the maximum stress or the major stress that you are going to calculate. I'm going to show you. You will compare it with the strength of this weld so that you can determine if this weld will be able to withstand or to carry the stress that will be created there. Right, as you can see from this question here, we have to use, where is it? Yeah, we're going to use plane stress formulae and Morh's cycle. Good, so let's do that. The first question, let's calculate. Right, let's calculate normal stresses on X and Y phase. Firstly, let's start with plane stress formula. So we're going to use this formula. Right, now let's substitute stress X, stress acting on the X phase is going to be the 42. So remember, if we have element like this, we're going to call this one X phase. So the stress acting on this X phase, this is X phase, this one is 42. So this 42 is stress acting on X phase. And then the stress, this is the Y phase, this one. This is the Y phase. So the stress acting on the Y phase is going to be 140. So this is Y phase. So this is X phase. So this is stress acting on the Y phase. Now stress X is tensile is going to be 42. We take tensile as positive, compression as negative. So plus is tensile, minus is compression. Plus stress Y is compressive. It's negative 140 over 2 plus 42 minus negative 140. This theta is going to be the angle of rotation. So the angle of rotation is 48. So as you can see from this formula, we have to multiply it by 2. Then you must be careful here. Common mistake here. So some of you will take this thing as cos 2 times 48. This is wrong. This one is right. So be careful. So with this one, it's like you will take cos 2 multiplied by 48. With this one is cos of 2 times 48 degrees, which is the cos of 90 something degrees, cos 90 something degrees. This one is cos 2 multiplied by 48 It's cos 248 times. So which is wrong. So you must put these 2 and the angle inside the bracket. That is the right way. So be careful there. Shear stress. Right, here as well, you must be very careful. You must be very careful. So the shear stress will either be negative or positive. Shear stress will either be negative or positive. So let me write it somewhere. I can write it here. We take anti-clockwise rotation as positive. We will use this thing for the angles and for the shear stress. The angle as well the theta can be positive or negative. So this 48 is positive. Why? Because they said that we are going to rotate the element anti-clockwise. So anti-clockwise is positive. That's why we made this thing positive. So this direction will work for shear stress, this one here, and this theta here. So we take clockwise as negative. So to determine whether the shear stress is clockwise or anti-clockwise, you go back to the element. So when I check on the element, when you check on the X face, you will see this downward line. Okay, as I've said this thing from the previous video, this thing, it has a meaning. This is the shear stress on the X face. So that's why I'm only going to consider this arrow on the X face. Remember from the element, we have an arrow like this. This is the shear stress on the Y face. We write it like this. This is the shear stress on the Y face in X direction. So this one is the shear stress where on the X face in which direction? In Y direction. Y meaning vertical direction. So as you check on this formula is shear stress XY. So meaning that we are talking about this arrow here. We are talking about this one. We are not talking about this one. This one is shear stress YX. So this formula, it's showing us shear stress XY. So we're always going to consider the X face. When we determine the direction of this shear stress, we're always going to consider the X face. Right, so let me remove this to avoid confusion. Always, you just have to check on the X face. Then from there, you will determine the direction. You can use this arrow alone. Remember, this one is still X face, this side. When you check on the other side, you will see an upward arrow like this. Right. So what is the direction here? So if you have something moving like this, like this. What is this direction? Is it clockwise or anti-clockwise? When you move like this is clockwise direction. So this is clockwise direction. So because this direction of this shear stresses on the x-face is clockwise, then that's why our shear stress is going to be negative. For clockwise direction, we use negative. So when we go back to substituting here, when we continue here, we're going to have plus is this plus is this one, plus shear stress on the x-face in vertical direction is going to be negative 60 sine 2 times 48. Then you calculate there, you will get this negative 118.183 MPa. So that will be the new normal stress after rotating this element by 48. So basically it's going to be this stress here. It's going to be this stress here, 118.183. So sometimes they will ask you to show these stresses on a sketch orientated at this angle. So they will be referring to this sketch here. They will say show stresses on a sketch orientated at this angle. So you can draw that thing like that and then show the stress values together with the angle. Remember, if we rotate it clockwise, it will be like this. Then if you rotate it anti-clockwise, it will be like this as you see it there. Now let's find the stress on the y face. This is y face. The normal stress on this face, which is the y face. Yeah, so this is the formula you substitute. Remember we said that the shear stress on the x face is going to be clockwise, and clockwise is negative. So that's why we're going to have negative. Good. So just for in case that you understand the direction of the shear stress, let's say this is just for an example. Let's say you have a set, we have the element on this side, you have an upward arrow. Remember from our problem we had downward arrow. Let's say you have an upward arrow. So if you have an upward arrow like that, if you move around this element, around it in this direction, like this, going like this, what is this? This will be anti-clockwise direction. Or if you can fix this thing here and then push this thing from up like this thing will rotate in an anti-clockwise direction. So anti-clockwise direction will be positive. meaning that if you have an upward arrow on this x face, on the right hand side, of this element, remember x face will have two sides, this side here and this one, but you must focus on this the right hand side of the x face. If you have upward arrow, the shear stress will be positive. If you have downward arrow, shear stress will be negative. Right, you substitute. This is what you will get after substituting. So that will be the shear stress value for here. 84.2. That will be the shear stress after rotating the element. So you can see you got the negative answer there, meaning that this arrow will still go down, will still go clockwise. Remember, negative means clockwise, so meaning that this arrow will still go downward. If you got positive answer, it means that this arrow will go in opposite direction. So this is the formula for calculating the resultant stress. I will show you at the later stage where is it coming from when we meet Morh's cycle. So now let's find the angle. So this is the angle of resultant. It will make more sense when we check it from the Morh's cycle. Right. I think now let's also find these values using Morh's cycle. Okay. From Morh's cycle, the first thing that you need to do now is to find before you can draw this, let's find the center of our cycle. So the center of our cycle will be equals to the average. Let me write it here. Will be equals to stress average. Center of our cycle will be equals to average stress. So average, if we have two stresses, you just have to add those two stresses. And then if there are two, you add them and then we divide by 2. So this will be equal to 42 negative 49 MPa. So make sure that you take the signs or the nature of the stress into account. Like don't just say 140. Remember 140 is compressive. So because 140 is compressive, that's why we have to put negative there. So let's mark our 49, 10, 20, 30, 40, 49. Yeah, so this is our 49. This is the point of the center of our cycle. Now we're going to have two coordinates, but from those two coordinates, you don't need both of them. You just need the one from the x face. So you can use both of them, but there is no need. If you can get uh, the ones from the x face, then that will be okay. Meaning that you have to check the stresses acting on the x face. So if I draw this thing temporarily, I'm going to remove it. From our x face, you will recall that we had something like this on the x face. Right, you know the coordinate from mathematics, it's x, y. So as we said, this line, horizontal line, is going to represent the normal stresses. This vertical line is going to represent the shear stress. So horizontal, its normal stress is 42, and then y, its shear stress, our shear stress, it's 60, but since it's clockwise, then we're going to have negative 60. We said that this thing is clockwise. So now we have to find this point. It's no longer centroid now. This thing I just wrote it. I wrote C because of that thing of coordinate. Represent coordinate, not centroid. So let's find this point. Okay, as you can see on this side is negative. If the shear stress is negative, then you're going to plot it on this side. If the shear stress is positive, you will plot it underneath. So clockwise, which is negative. So if the shear stress is clockwise, it means that it's negative. Then we're going to plot it here on top of this horizontal line. So we have negative 60. That's why we don't plot. We're not going to plot that 60 below this horizontal line. Below this horizontal line is positive shear stress. So now we have negative shear stress. So that's why we plot it above. So here is your 60. You can draw a dotted line from here. And then come here and find the 42. Okay, let's also mark it. Okay, 42, let's mark it here. Yeah, you can draw a construction line. Then where they meet, it's going to be this point here, this one. So I said that you don't really need to use the stresses on the Y face as well. You just need these stresses on the X face. Then you will just have to project that line. Right. So from here, you need a compass. Here we go. So remember our center is here, 49. So you must put this edge, this other leg of your compass on that point of 49, and then stretch this one. It's too short. It's too short. Yes, yes. Let me make another plan. So this compass is too short. Yeah, but anyway, what you have to do, you have to stretch this thing until it touches this dot here. Then once it touches this dot, you stop. Then from there, you scribe. You scribe a cycle like this. Okay. Right. You're going to have something like this. This is what you are going to have. Yeah, you place your ruler like this. From this point here, which is the coordinate on that X face, and this point here, this is the center, is that 49. Hope you still remember. So make sure that the line that you're going to draw is going to cross here at 49. Almost. Right, that's it. Yeah, it should correspond with 140. Remember on the X, on the Y face, you have 140, and then you have no shear stress at 60, you have 140. It's compressive. So that's why this point here, it has to be the coordinate on the y face. On the y face, this coordinate is compression negative 140. That's why from here, we'll see from here to there, it's negative 140. Then this 140 should correspond with 60 clockwise. So the shear stress on this y face, it's 60, check this direction. On the other side of the y face, it will be like this. So this kind of movement, this is anti-clockwise, and anti-clockwise we take it as positive. So that's why we're going to have positive shear stress. Then because we have positive shear stress, that's why we have to plot the shear stress below, from below this horizontal line. So positive shear stress is going to be somewhere there. Yeah, so that should correspond with positive 60 from underneath. 60 hopefully it will be somewhere here, and then 60 will be here, and that 60 together with that negative 140, they will give you this point. Right, from here we need to rotate this line, this principal plane line. So remember, now we're using Mohr cycle. So from the Mohr cycle, they said that we have to rotate the element in an anti-clockwise direction at an angle of 48 from the horizontal, which is that x face, which is from that x. So actually our reference, we're going to always make our reference to be x face. So check, I said this, remember from here to there, or this point here, we've used this 42, which is from the x face, and this one, which is from the x face. So that's why now from here to there, we can say it represents the x face. So now we're going to take this x face, or we're going to take this line, our reference being x face. We're going to rotate it from x face, meaning that we're going to measure from x face. We're going to rotate this thing in an anti-clockwise direction at an angle of 48. But remember, in terms of angles, when it comes to the Morse cycle, the angle will multiply by 2. So check here. This one is this coordinate here, this one and this one. This is the coordinate of the y face. On the y face, we have this normal stress, and then we have this shear stress. So we can say this one is the y face. So this is the x face. This is the y face. Check on the element. This is the element. Check on the element. The y face and the x face, they are separated by 90 degrees. But when it comes to Mohr cycle, the x face and the y face, they are separated by a straight line or by 180 degrees Celsius. So that means from element, this angle on the element is 90 degrees. Angle between y and x is 90 degrees. When it comes to Mohr cycle, it's 180. So from element, if you rotate element by 20, you must rotate it by 20 times 2 on the Mohr cycle. So what the angles multiply by 2 when it comes to Mohr cycle. From element to Mohr cycle, you multiply the angle by 2. So remember that. So that means we're going to rotate this element or this plane by an angle of 48 times 2. Uh, 48 times 2 is how much? You will forgive me. You will forgive me. Let me just write it here. Angle of rotation equals to 2 times 48. 96 degrees. They already told us the direction, it's anti-clockwise. So we're going to rotate this plane by an angle of 96 degrees Celsius. Sorry, not Celsius. 96 degrees from the x-face. Our x-face is our reference, meaning that at this on this line, the angle is 0. So we're going to measure from this x-face. The angle will be 0 here. Then from there, we measure an angle of 96 in which direction? In an anti-clockwise direction, meaning that we are going to measure from here going in this direction. This is an anti-clockwise. If it was clockwise, we were going to measure that angle going down. So we know that now to measure angles, we need a protractor. Yeah, you must put it at the center of this cycle, which is at 49. I think it's okay like this. So from this, you have to, oh, sorry, no. The way of positioning it now is like our 0, as you can see, 0 is here. 0 is on this line, is here. Is here. No, I said the reference must be that X face. So I must arrange this thing in that way. So I need to rotate it. This blue line for, let me remove this. Right. Good. Good. So our 0 now is on this X face. That is good. So we're going to measure an angle from here, which is 0, 96, going in that direction, in an anti-clockwise direction. So we'll have 10, 20, 30, 40, 50, 60, 70, 80, 90. What is that angle? 96. So this is 95 here. So 96. 96 will be somewhere here. That will be 96. 96. So once you measure that, we've measured that 96, you can move this protractor here. So the angle from this x face line, which is 0 to this, it's 96 degrees. So now I can just extend this line. Yeah, not that perfect, but yeah, almost. So this is the line at an angle of that 96. So let's project it until it meets the circumference of the circle. You do the same thing on this side. Yeah, so like that. So what did we do here? We took this black line and rotated it at an angle of 96 in an anti-clockwise direction. So after rotating it in an anti-clockwise direction at an angle of 96, we're going to have this sky blue line. We're going to have this sky blue line. So now we have to find the stress that will act on this sky blue line. This is the line after, or the plane after rotating the element by 48. This is the plane, this blue line. So we have to find the stresses acting on this plane. So to find the stresses, which is the shear stress and the normal stress, we're going to measure from the point of origin, from here, from this 0, 0, this point of origin, from here to there, but horizontal distance. Remember, normal stress is represented by a horizontal measurement or distance. So you have to measure from here horizontally to there. That will be the normal stress on this plane, which is the x plane. Remember, we took this x face, this line which is x face, we rotated it like this, we moved it, meaning that the x face will also move from here to there. So this is still an x face. So this is the x face after rotation. So we normally can just put x prime. This one is just the x. This one is x prime, meaning that this is the x after rotation. So the same thing with y. As we rotate this black line, this y as well will move from here to there. So this will be y prime as well. So if you want to know the new stress after rotating the element by 45 on the y face, you will have to measure from here up to there, but horizontally. Okay, let's measure those stresses. So I don't know, you can approach it or we can measure it differently. So you'll take your ruler like this. Yeah, like that. So this is, we measure from here to there. This one. This will be the new stress after rotation on the X phase. How much is this? I see about 11, 11.5, 11.7. Yeah, about 11.8. It's what? Centimeter. But you will have a scale saying that what? The scale will be saying what? 1. Hmm? Yeah, your scale will be, remember, from here to there, is 1 centimeter. So 1 centimeter equals to 10 MPa. From here to there is 1 centimeter, but this 1 centimeter represents 10 MPa. So after getting the centimeters like this, you have to convert them to MPa. So you'll do that by multiplying by 10. Multiply back by your scale. So that will be the normal stress on the X phase. Then you come back again to the normal stress on the Y phase. Let me project this line here. Come with your ruler, measure from here to there. How much? It's almost 2 centimeter. So you measure from here to there, which is almost 2 centimeter. So this will be stress Y bar. 2 centimeter multiplied by 10. 20 MPa. Right. So remember we got the very same values. What are those calculations? We found 118. it's negative. Then on the x face we found, on the y face we find the 20 is positive. So this is exactly the same thing. So remember this 118, this point is on the left hand side. On the left hand side is compression, or is negative. That's why it's negative 118. And then this one is on the right hand side. On the right hand side we have positive normal stresses. That's why it's positive, positive 20 there. Now let's check shear stress. Shear stress, we know that is represented by this vertical line. Normal stress are represented by this horizontal line. That's why when we measured the horizontal and normal stresses, we've used horizontal lines. But to measure the shear stress, we're going to use the vertical line. So shear stress, we're going to measure from this point of origin, from here to there, at the vertical distance, vertically. So for shear stress, it will be up to you. You can measure from this origin to here. You will get the same answers. Your answer will be the same. But let's deal with, just focus on the x face. So we're going to measure the shear stress from the x face. Yeah, here we go. It's about 84 point something. You measure from here to there. Actually in centimeters is 8.4 something. So measure from here to there. As you can see from this ruler, you will have this will represent the shear stress. About 8.2. Oh no, 84.2. That will be the shear stress. So it doesn't matter, you can even measure from here to this origin, point of origin to here, but vertical distance from here to here is still the same thing, 8.4. But as I've said, stick to the x face. Negative 84.2. That's what we got. So as I've said, we use x face. So you can see now the shear stress on the x face from here to there is negative 84. Why is it negative? Remember, these values here are the negative values. So this is negative 84 on the x face. So the shear stress on the x face is negative 84. On the y face will be positive 84. But these formulas, they are automatically going to give you the values on the x face. So that's why we had the negative there from the formula. Now let's go to resultant stress. So resultant stress, you will have to measure from this point to there. Before I release this case, just check there. This thing already measured for you there. It's about 14.5. Hopefully you can see that. It's written for you there 14.4, 14.5 centimeter. So meaning that this line from here to there is 14.5 centimeter. So that will be the resultant stress. Resultant stress, you measure diagonally. Remember, shear stress we've measured vertical distance. Normal stress we've measured horizontal distance. Resultant stress we measure diagonally at an incline. From here to that point is 14.5. So this will be this red dotted line. That will be the resultant stress. So resultant stress is 14.5 centimeter. So multiply by 10 is going to be 145 MPa. So let's see how much we got. Exactly this, we got 145 MPa. So now let's check the angle of this resultant. From the calculations we got 35. So let's see how much we're going to get. We got 35.5. Here we go. Check this red dotted line is crossing between 30 and 40. Between 30 and 40. So it's 35, maybe 0.2. Yeah, 35.2. That's what I'm getting from the protractor there. Protractor. So yeah. So that beta from graphically, I'm getting 35.2 degrees Celsius. Good. We're getting the same values. We're getting the same values. Right, the next question is to calculate the principal stresses and the planes where you will find those principal stresses. Remember, when we are talking about the principal stress, or let's say principal plane, when we are talking about the principal plane, we are talking about the plane where there is no shear stress. So if it happens that on this y plane, the shear stress is 0, then we're going to call this plane a principal plane. Why? Because shear stress is 0, there is no shear stress. Then while the shear stress is 0 like that on this plane, while the shear stress is 0 on this plane, if you find that there is a stress acting on this plane of 0 shear stress, then we're going to call that stress principal stress. So any force or stress that acts on the plane where the shear stress is 0, that stress we're going to call it the principal stress. So in our case, as we rotate this element, as this element gets rotated, there will be a certain point where the shear stress will be 0. There will be a certain point where the shear stress will be 0. And then at that point, immediately at that point, if the shear stress is 0 when the element is at this angle, it means that those stresses that will act on this plane at that angle where the shear stress is 0, these stresses we're going to call them the principal stresses. So now we have the formula to find the magnitude of those principal stresses and the angle at which we're going to find those principal stresses, or the angle at which when you rotate this element the shear stress will be 0. So we're going to have the formulas for that. So we're also going to find those planes or those stresses using the Mohr cycle. For now, let's use analytical method. So I'm going to write the formula down. Substitute. We know why the shear stress is negative. Even though normally this one, negative or positive, it won't have effect since we're going to square it. But always put that negative if it's negative shear stress to show that you understand. So that is principal stress number 1. So according to the formula, that is, those are our principal stresses. Right, so let's go to Morh's cycle and find the principal stresses. Here we go. Principal stresses will be here. This is the point of 0 shear stress. At this point and at this point, there is no shear stress. So, since there is no shear stress at this point of the cycle and at that point, then these points are going to give us the principal planes and the principal stresses. Remember, on this point of the cycle, this point represents normal stress and the shear stress. in the element, if it's rotated at a certain specific angle, even this point here, it represents the state of stresses in an element inclined at a certain angle. So yes, at this point, there will be shear stress. If you want to know the shear stress at this incline, you measure from here to there. If you want to know the shear stress at this point, you measure from here to there. The same thing if you want to know the shear stress at this point, you measure from here to there. But at this point, there is no vertical distance between this brown dot and this black line, or between this brown dot and this point of origin. There is no vertical line between those two dots. Remember, the vertical distance or vertical line represent the shear stress. So that's why there is no shear stress at this point and at this point. So since this stress at this point, you'll only find one stress, which is normal stress. That normal stress is going to be the principal stress at the same time, since there is no shear stress. So in short, always the principal stress, we're going to find it here on this horizontal line from this origin. From this origin, you draw the horizontal line. Where the horizontal line meets the cycle, we're going to have, that's why you're going to have the principal points and the principal stresses, or the principal planes. So the principal stress 1, always measure from this origin point. Principal stress is going to be from here to there. So as you can see, from here to there is going to be 60. It's positive. So we know on this side is 10 sides. Then principal stress number 2 is going to be from here. You measure from here horizontally to here. How much is this? Length from here to there is about 15.8 centimeter. Multiplied by 10 is 158. Yes. You can see this is 150. This is 160. 150, 160. So somewhere here will be 158 MPa. So that's all for the principal stresses. Yeah, the stresses must always balance. Normal stress before you rotate the element, and the normal stress after rotating the element, and the principal stresses. The sum of those stresses, they should be equal. That is due to the fact that when one increases, the other one decreases. When then normal stress on the X phase increases, the normal stress on the Y phase decreases, and so forth. The same thing with energy conservation, the law of conservation of energy. When one loses maybe the potential energy, it gains the kinetic energy, and so forth. So that's why we say that the total energy will remain constant. The same thing with these stresses. The sum of these stresses during the transformation, the sum of these stresses will remain the same. So you will have 42 as normal stress plus that compressive stress of 140. When we add those two stresses, it should give you the same thing as when we add these ones. So all these three stresses, the sum of those two will give you 98. So that means your stresses are right, are well balanced. Right, now to find the theta p, which is the angle to reach the principal plane. The angle to reach principal plane, we are going to measure from this black line to the horizontal axis. So in other words, remember this line here, we said that this is the principal plane, or this is where we're going to have principal stresses. So now we want to know the angle at which we must rotate this black line so that this black line can reach this principal plane. For this line to reach this principal plane, or the plane where there is no shear stress, we must rotate this line by this angle. So this angle, we're going to call it theta p. So just to give you an idea of this formula, to calculate this theta p, we are going to use this formula, this one. But just to give you an idea of where it's coming from, it will be, you can consider, let me use a different color. You can consider this blue triangle, this one. So remember, from here to there is the shear stress. How much is that shear stress? Is that shear stress of 60? If you still recall. As you can see, from here to there it's 60. Is that 60 that is given, or that we got from the original element before rotation? So now the problem is to find the distance from here to there. We're going to find theta p. To find theta p, we're going to use tan theta p equals to opposite side, which is stress xy, divide by, we have to divide by this side from here to there. So now to find that distance from here to there, we have to find this whole distance starting from here to there. So this distance from here to there will be given by stress x minus stress y. So that is the general formula. But if you can check the distance from here to there plus the distance from here to there these two distances, they will give you that total distance from here to there. So the distance from here to there is that 42. And the distance from here to there is that on the Y face, how much was it? Is that 140? Sorry, I was looking for the wrong thing, yeah. I wasn't supposed to use this. Oh, yeah, sorry for that. I was supposed to use this one. Yeah. Okay, if I may start again, you consider this triangle, but which is identical to this one here. So the distance from here to there is going to be this one. So now we want to find this distance from here to there. So to find this distance, we must firstly find the total distance. Let's find the total distance from here to there. Why this thing is no longer writing? Find the distance from here to there. After that, we'll divide it by 2. So what I was saying just now is that to find this total distance from here to there, you'll say from here to there, it's 42, as you can see from the sketch. From the origin to here, it's 140. Remember this point, X point, or the horizontal point is corresponding with 140 there. 140. So to find this total distance, I can say distance so stresses from here to there, it will be that stress X plus stress Y, which is that 140 plus 42. That will be the total from here to there. But we want from here to there. So you'll take that divided by 2. Since this distance here equal to this distance, you divide it by 2. Don't get surprised on the formula when you see this. Remember, it will start like this, but it will be this minus. Then stress Y is negative. Then mathematically that will lead you to this. So which is that part there. So theta P will be this side divided by this side. So to get that theta P, we're going to use this formula. So this 2 here, actually, it's this one here. It's that adjacent side that I've just shown. Right. So you substitute, you will get 2. Shear stress is negative 60. 42 minus 2 theta P will be equals to the inverse, tan inverse of this. So which is going to be you calculate there. So this is 2 theta p, which is this angle here. This angle starting from here to there, it represents 2 theta p. So y is 2, we know that on the Mohr cycle, the angle from the element to the Mohr cycle, it will be multiplied by 2. Now, if you want to know the angle on the element, theta p, you will take this divided by 2, which is 16.7 degrees. What does this thing mean? Okay, it means that from this plane, this black line, to the principal plane, you have to move or you have to rotate this thing. When you rotate this line from here to there, you will be moving in a clockwise direction. That's why our angle is negative. Clockwise means negative. So it means that to move from here to there on the Mohr cycle, to move that black line from here to there, you must rotate this black line clockwise. That's why our angle is negative. At an angle of how much? At an angle of 33 degrees. Check this angle here. Just that now there is too many things here. But hopefully you will see. It's the wrong line. So check this angle from this to there. Check, this is 30 here. 32, 32. That black line is after 33. So this angle here, from the protractor there, it's 33 point something. 33 point something, or you can leave it as 33, it's still okay. But 33 maybe 0.4 degrees. So that means to move this line to this plane where there is zero shear stress, you must rotate this line in a clockwise direction by this angle of 33. So this is what we got. So that is what you must do on the Mohr's cycle, you must rotate this element by 33. But on the element, we're not going to rotate this element by 33 to reach the point of maximum shear stress. Well, on the element, we take this angle divided by 2. So that's why on the element, we are going to rotate the element by sorry, this is anti-clockwise. So it has to be clockwise since you got the negative answer. So we have to rotate the element by clockwise. That's why we have negative there by 16.7 degrees. And at this plane, we are not going to have any shear stress. And the normal stresses will be those principal stresses. Those principal stresses of 60 and 158. So you will have this plane and this plane here. These are the principal planes. So if the angle from here to there is 16, how much will be the angle from here to there? It's going to be this angle which is that 16 plus this angle here which is 90. So 16 is from this here, from X. This is our reference. It's from horizontal to this plane number 1. And then plane number 2 is this one. So on here, the shear stress, on this plane, shear stress will be 0 as well. So on these two planes, the shear stress is going to be 0. So on element wise, theta what can I call it? Let me say P1 is going to be 16.7 and theta P2 on plane number 2 is going to be 16.7 plus 90. Sorry. Yeah, you have to take that angle direction into account. So since it's clockwise from here to there, clockwise, you must put negative there. You will get 73.3 degrees. So we have two options to reach that principal plane. The other one is this one. So back to this. Remember, we've got two principal planes. This one here, this side, and this one. Even here, the shear stress is 0. So it's either you rotate this black line to here by 33, or you rotate that black line in a clockwise direction to this side. So we'll have two options. You can rotate this black line in an anti-clockwise direction with this angle of, you'll see the angle from here to there, it's 147. It's 147. So calculation wise, which is this one. Then we got positive answer here. So that positive answer is this one. Remember I said this one you rotate it anti-clockwise, and then we take anti-clockwise as what? As positive. This one you rotate clockwise. That's why we got negative 33. So it's just two options of making sure that this black line lies on this horizontal. So it's either you rotate it like this or like that. And then that 147, this one will happen on Mohr cycle. But on element is theta p. We'll take this divided by 2. It's 73. Uh, 73 point what? 0.3. It's positive. Positive means anti-clock. Right, let's check maximum shear stress. So remember, we're going to rotate this thing. You will find that when we rotate this element by a very small angle, the normal stress and shear stress at this angle will be represented by this point. So as you increase the angle from 5 degrees maybe to 10 degrees, the shear stress and normal stress at 10 degrees maybe will be represented by this point. So as you increase the angle to 30 degrees, then the shear stress and the normal stress at that angle of 30 degrees maybe will be represented by this dot here, and so forth. So this point represents the shear stress at different planes or inclines or angles, like this. So the shear stress at this point will measure the vertical distance from here to there. Shear stress at this point measure vertical distance from there to there. Shear stress at this point, and so forth, and so forth. If you want the shear stress here, you draw a vertical line from here to there. If you want shear stress here, you draw a vertical line from here to there, and so forth. So you will see that from here to there, this line, the length of this line increases. From here to this one, the line increases, meaning that the shear stress increases as you rotate this element like this. When you check from here to here, the shear stress starts to decrease. This length starts to decrease, decreases up until here. Here is going to reach 0 here. So it starts from 0, increases. At this point, we are going to have the maximum shear stress. You can see this line from here to there is the longest compared to the rest of these vertical lines. So this is where we're going to have the maximum shear stress. Then the maximum shear stress always on the element, you will get it when you rotate the element by 45 degrees. But when you go to Mohr cycle, you take that 45 multiplied by 2, it will be 90 degrees. So at 90 degrees from the X phase, from horizontal, you will get the maximum shear stress. So the maximum shear stress occurs at that angle of 45 degrees. Or maximum shear stress will be maximum at an angle of 45 degrees on the element. So on Mohr cycle, it will be at an angle of 90 degrees. So now you can see that this distance from the center to the circumference is what? Is a radius. From here to here, it's a radius. So that's why the maximum shear stress equals to the radius. So on the formula sheet that you use during exams, somewhere they wrote R. That R is the formula for the maximum shear stress. Or they will give you this formula. This is the formula for maximum shear stress. Maximum shear stress which equals to the radius. So please don't confuse that R with the resultant stress. So most of you, when they say calculate resultant stress, you are going to use this formula. The formula for resultant stress is this one. It's this one. It's not there on your formula sheet. That means maybe you have to memorize it. Yeah, but you don't have to memorize it. You have to understand it. I will show you just now. So just be careful. On your formula sheet, R, that R is for maximum shear stress. This formula is there. They've equated this to R. So don't confuse it with the resultant. So where is this one coming from? So to get this R here, we're going to use this triangle. Let's consider this triangle. Remember, from here to there is what? Is R. From the center to the circumference is R. From here to there is R. So the R that I'm going to use is going to be this one, not this one. But we know that this radius equals to this one, this radius. So from this triangle, this distance from here to there, I spoke about it. I'm not going to explain it again to save time. It's that one of stress x minus stress y divided by 2. It's this distance from here to there. So this distance from here to there is the shear stress. From here to there is the shear stress. So now this is 2 theta s. So to calculate this angle 2 theta s, you will say tan equals to opposite, which is this, divided by the shear stress. Divided by the shear stress. So when you simplify this, oh, I didn't write that formula down. Okay, anyway, when you simplify that, you will get this. So this one is for direction, clockwise or anti-clockwise. But it will always be negative here. I will show you at the later stage. But always, whether clockwise or anti-clockwise, this is formula. It will always be like this. Right, I was just showing you where is that formula coming from. Actually, what is this? Why are we calculating this angle? So this thing is like this. For this plane, for this black line to reach the plane of maximum shear stress, this black line that I'm drawing now is the plane of maximum shear stress. So to move this line from here, this black line from here to this maximum shear stress plane, you must rotate this line by this angle. So the plane of maximum shear stress is this. For this to reach the plane of maximum shear stress, you must rotate this thing by this angle. So to calculate the shear stress, maximum shear stress, I've explained that formula. So you will substitute it there. To save time, this video is too long. Find the maximum shear stress. You substitute, you will get that the maximum shear stress is this much. So let's go and verify it using Mohr's cycle. You got 109. So you must measure from here yeah, that point of origin now is no longer that visible. It's yeah, it's somewhere there. Good. So you will see from here, from that point of origin to here is about, this is 10 centimeter. This is 10.9 centimeter. This is what 11 centimeter. So it's 10.9 centimeter. So this thing is going to give you the maximum shear stress. So the maximum shear stress multiplied by 10. Then you will get that 109 MPa. That will be the maximum shear stress. Then the last part, to find that angle there, that you must rotate this plane to reach that plane of maximum shear. You use this one, this formula here. Yeah, so that is the angle. Remember, actually always they will want to know the angle of rotation for the element, not on Mohr's cycle. So this one is for on Mohr cycle, but on element you divide those angles by 2. So always we have to find these ones for element. Okay, on Mohr cycle, it means that this angle from here to here, if you want this line to reach the plane of maximum shear stress, which is this line, you have to rotate this angle by this line by this angle of 2 theta s. From the calculations we got 50 what. So now let's see graphically when we measure this thing ourselves. Right, I think that is the right point. Okay, the line of maximum shear stress, it has to be from the point, from the center of our cycle. From the center of our cycle, we draw a vertical line upward. That will be the maximum shear stress line, or that will be the plane of maximum shear stress. Right, now we have to measure this angle from here to there. So this is 10, 20, 30, 40, 50. This is 50. 55 is this one here. That black line, there's almost 57. It will almost be about 57 or 56 point something. So it's this one, 57. Or the other way, remember you must use a ruler here. Remember, even from the point of origin, from here, using a ruler vertically downward. This is still the plane of maximum shear. The shear stress is maximum here. So you have two planes actually. So the first plane is this one. This one. Second one is this one. So to move this one to this maximum shear stress plane, the plane of maximum shear stress, you must move by the angle of 57. To move from here to there, which is for plane number 2, you must say 57, this angle here, which is 57, plus this angle of straight line, which is 180. So that angle will be this one. So on Mohr cycle, to move this plane from here to here, you must move by that angle of 57 plus 180. That is on Mohr cycle. And then on the element, you take that angle, divide by 2, you'll get this. So you can see these answers here, both of them, they are positive. So that positive is what is anti-clockwise. That's why you see here, from here to there, you are moving anti-clockwise. From here to here, you are moving anti-clockwise. So that's why even those angles are positive. Yeah, so yeah, I know this video is too long, but I didn't have a choice. Actually, I had to cover two sections, or I had to cover one chapter. So yeah, actually still a little. One chapter in 2 hours is still not enough. But trust me, I've covered everything that you need to know from this chapter. I've covered the Mohr cycle. I've covered the calculation twice, or the analytical method. Actually, we have analytical method and the graphical method. And also make sure that you watch the first video. As I've said, that the first video is even more basic, or the introduction part actually is there in in the first lesson. So this one actually is the second lesson. Yeah, so thank you very much. I hope this will be very fruitful. Thank you for watching.